Recording, we're looking at the relationship between the sum of the roots and the product of the roots, and looking at the graphs that give us some of the information that we can use, or that we might be asked to sketch as part of the work. So let's have a look at some examples. Example 1 is the parabola y equals x squared minus 4. So here's our parabola. We know that the roots are negative 2 and 2. So if we call the roots alpha and beta, now it doesn't matter the order in which these occur. We could say alpha is 2 and beta is negative 2. That's irrelevant. But the sum of the roots is 0 because negative b over a, in this equation, b is 0 anyway. So the sum of the roots is 0. The product, as you can see, is negative 4. In the equation for our parabola, the product of the roots is the second term anyway. And so the link between the roots and the constant term at the end of the equation is the product of the roots. Let's look at the second example at the same time. Here's the equation y equals x squared plus 4x plus 3. Now our roots, by looking at the sketch, are negative 1 and 3. If we were to factorize this, you would have x plus 3x plus 1, and that gives you the roots anyway. Sum of the roots is negative 4 because negative b over a is negative 4 anyway. And here again, the constant is 3 and the product of the roots is 3. Example 3. Now example 3, I'll turn these ones off now, is not a monic quadratic, so it's not a coefficient of 1. So slight difference here, that our roots again are these values here. If we factorized this, we would have 2x minus 1, x minus 2 as the two products. Negative b over a is 5 over 2, which is 2.5. There's 2.5, and the product is 1. So the product of the roots isn't equal to the constant unless this is a monic expression, and you can see c over a is 1 anyway. So again, you can see by the graph, if you're asked to graph this, don't forget all of this, the axis of symmetry is negative b over 2a, so we're halfway between those two things. Okay, looking at example number 4. Just another example, but I suppose what I want to point out here is we could express this as one root is double the other root. So I could have here alpha as this root and 2 alpha as the second root. Again, it doesn't matter if I call these both alpha and 2 alpha or call them beta and 2 beta. We can still work out the sum of the roots. In this case, we would see that alpha plus 2 alpha is, it's actually negative 6. There should be a negative there. And there's the product of the roots. So there's where you'll see one root is the double of the other. Here is an example where we have one root which is the inverse or reciprocal of the other. Okay, we have negative 2 and negative 1/2. Again, product of the sum of the roots is negative 2.5 and the product is 1. Okay, so there's nothing particularly exciting here, just looking at some of the ways in which we might express questions on a paper. In this example, here we see that now we have roots which are the negative reciprocal of each other. The roots here are 4, negative 4 I should say, and 1/4. Okay, here's the sum of the roots, negative 3.75, which is negative b over a. Product of the roots is negative 1. The last example I'll look at has the same roots, and again is one root is the reciprocal and negative of the other, but in this case I've just made the whole thing negative, so we have a concave down parabola, same roots, basically the same equation except negatives the whole way through. Well, sorry, each term has been made negatives, which is why we have a plus here. Works the same way. Negative b over a gives us this value here, positive, and the product is c over a. Okay, so there's a range of examples, both looking at the graphs. So we can start with this information and sketch the graphs, or we could start with the graph and be asked to find the sum and the product of the roots. And if you look at the roots and the values of the roots, you can find these values and then find the equation as well.